Hello everybody, good afternoon. This is Tasen. I am happy to be here again. Welcome to Mathify Analytics. Today I am super happy because today is my birthday. I am celebrating. Who is celebrating with me? If you are celebrating and you are thankful because of the gift of life, say amen. Let's celebrate. I'm celebrating. So as a part of celebration, I have decided to solve one question. Isn't it a good gift? Yes. So let's celebrate. I hope you have been enjoying our videos anyway. So if you like our videos, don't forget to click like and share the videos to your network. If it's your first time to be on this channel, please don't forget to subscribe. Don't go without subscribing. Subscribe and turn on the notification bell so that you'll get notified anytime we upload a new video. Yes. So we are going to solve just one question because I can't just sit down here on my birthday and solve many questions. I'm going to solve just one question for you. We are starting question number B, section number B of the questionnaire that we started, and today I'm going to solve just one question number 16, and then we will continue next time. The question number 16 was about studying a function, and when we are studying a function, we need to know its domain of definition, maybe some asymptote if they exist. We start the first derivative and the second derivative and the table variation, and then sketch the function. So let's go through all these steps for this particular function that we were given in this particular exam. So the function was f of x. Yes, it was f of x, this is x, equal to 1 over 2 x squared e power x plus 1. And A, we were asked to find the domain of definition. Let me say that the domain is D. So the domain of definition for this function, you can see that for nx in R, x squared is defined and e exponential function also is defined. So the composition of these two functions, this function and this one, it will be also defined for any value in R. So the domain of definition for this function was supposed to be the set of real numbers, R, from minus infinity to plus infinity. So that was A. And question number B, it was asked to compute the asymptotes if they exist. First of all, the vertical asymptote doesn't exist for this function. Why? Because the function is defined in all the values of R. So since it is defined for all values, it doesn't have a vertical asymptote, because the vertical asymptote exists for any point which is not belong in the domain of definition. So we don't have any vertical asymptote. So let's see if we have a horizontal asymptote. To have a horizontal asymptote, we should compute the limits when x tends to plus or minus infinity of our function f of x. So let's start for limit when x tends to let's start for plus infinity of f of x. So this limit will be equal to what? It will be limit when x tends to plus infinity of 1 over 2 x squared e power x plus 1. And this is equal to 1 over 2 infinity power 2 and e power plus infinity, of course, plus 1. So this is equal to infinity times infinity. Yes, right? Times infinity times infinity. This is not in the terminate form. So this is equal to plus infinity. Yes. We don't have asymptote, horizontal asymptote when x tend to plus infinity. In this case, the horizontal asymptote, when x tend to plus infinity, this horizontal asymptote doesn't also exist. But what about when x tend to minus infinity? Let's see. Limit when x tend to minus infinity of f of x. This will be equal to what? This will be equal to limit when x tend to minus infinity of 1 over 2 x squared e power x and plus 1, like this. So this will be equal to what? Yeah, this will be equal to 1 over 2 minus infinity power 2 and e power minus infinity plus 1, and this is equal to 1 over 2 times infinity. This is infinity. I can even clean this 1 over 2. Yes, this is infinity plus infinity, and e power minus infinity plus 1. This is e power minus infinity. This is equal to the same as 1 over e power plus infinity, and I mean only this one, not with this. So 1 over e power plus infinity, this will be equal to 1 over plus infinity. This is 1 over plus infinity, or which is equal to 0. So if we combine this and this one, then we will have infinity times infinity, which is in the determinate form. This is in the determinate form. So then we need to find a way to overcome this, to remove this indeterminate form. Can we proceed? How can we proceed? We can try to rewrite our function f of x. We have f of x equal to 1 over 2 e power, oh no, not e power, first x squared e power x plus 1. This can be written as 1 over 2 e from this one, e power 1, it's e, then times x squared and times e power x, like this. And this can be written again as 1 over 2 e x squared over e power minus x, like this. Oh, not infinity. E power minus x. Let me write it clearly. It's e over e power minus x, like this. So if I rewrite my function f of x in this form, like this, I will get another indeterminate form. Which is not infinity times 0, but which will be infinity over infinity, and it is easy to remove that infinity indeterminate form instead. So if we compute limit when x tend to minus infinity of f of x, in this case it will be equal to 1 over 2 times e times minus infinity squared and over e power minus then e power plus infinity. E power plus infinity, it's plus infinity, then we will get infinity over infinity. This is also indeterminate form, but easy to remove. How do we remove this kind of indeterminate form? We can use the hospital rule. Do you remember the hospital rule? Do you remember the hospital rule? We will get limit when x tend to minus infinity of our function f of x will be equal to limit when x tend to minus infinity of 1 over 2, it was e then x squared over, this is squared, let me write it well. Yes, this is x squared over e power minus x. And then we can use the hospital rule. If we use the hospital rule, we will get limit when x tends to minus infinity of 1 over 2 e. Then if we differentiate the numerator will be 2x, then over the derivative of the denominator will be minus e power minus x, like this. So then this will 2 and 2 will be simplified, and this will be equal to minus e and times minus infinity, yes, and over minus e power minus infinity, like this. This will be plus, this plus and plus, yes, and then this will be plus e power plus infinity is infinity. Then we get again indeterminate form, infinity over infinity. And we can again apply the hospital rule. Hospital rule again. If we apply the hospital rule for the second time, we will get the limit when x tends to minus infinity. Then we have to differentiate the function e x, because 2 and 2 has been simplified, over e power, we have minus here, minus, yes, e power minus x. So then we use the hospital rule and we differentiate this and differentiate this derivative. So this will be equal to limit when x tends to minus infinity of e, yes, because x derivative is 1, then over, then plus e power minus x. So if we replace x by minus infinity, we will get e over e power minus infinity, and minus will be plus, then will be equal to e over e power plus infinity. E power plus infinity, it's plus infinity, then this is e over plus infinity, and any number over plus infinity it's equal to 0. So we have limit when x tends to minus infinity of our function f of x is equal to 0. So what does it mean? This means that we have a horizontal asymptote at y equal to 0. So we get a horizontal asymptote of equation y equal to 0. So since we have a horizontal asymptote, there is no need to find the oblique asymptote, because the horizontal asymptote and the oblique asymptote cannot exist at the same time for one equation. So then oblique asymptote doesn't exist. When the horizontal asymptote exists, the oblique asymptote doesn't. So now we have find the horizontal asymptote. The vertical asymptote doesn't exist, and the oblique asymptote doesn't exist. We only have the horizontal asymptote at y equal to 0 when x tends to minus infinity. Yes, so then let's move on to the next question. The next sub-question, of course, the next sub-question says that we have to study the first derivative and the second derivative of our function and make the variation table. So let's start with the first derivative. Let me rewrite again our function f of x equal to 1 over 2 x squared e power x plus 1. So and then let's first find the first derivative. The first derivative of our function will be equal to 1 over 2 times 2x times e power x plus 1 and plus 1 over 2 x squared and e power x plus 1, because e power x plus 1 derivative is the same, e power x plus 1. and then this will be equal to 2 and 2 are simplified. We get x e power x plus 1 and plus 1 over 2 x squared e power x plus 1. This is the same as x plus 1 over 2 x squared and power and times e power x plus 1. This is the first derivative. F derivative equal. F derivative equal. This is the first derivative. Yes. Since we are aiming to find the variation table, we need to find the critical point for this function. Critical points. Let's find the critical points. Do you remember how we find critical points? We need to solve these derivative points to be equal to 0. To find critical points, we solve f derivative of x equal to 0. If we solve this function, we need to solve, then this is the same as solving x plus 1 over 2 x squared and times e power x plus 1 equal to 0. This cannot be 0. It is always different from 0. So our function is equal to 0, not the function. Our derivative is equal to 0 if and only if x plus 1 over 2 x squared is equal to 0. So this is the same as x plus times 1 plus 1 over 2 times x equal to 0. So if x is equal to 0 or 1 plus 1 over 2 x is equal to 0. This is the same as x equal to 0 or x equal to then minus 2. Yes. So we have these 2 points, x equal to 0. So then critical points will be, we need to find f of x equal to 0. This will be equal to, our function is 1 over 2 and then 0 power 2 times e power 0 plus 1. This is equal to 0 power 2 is equal to 0. So then this is equal to 0. Yeah. F of x equal to 0 is equal to 0, and f of x equal to minus 2 equal to what? So from this we get the point. The first critical point is first critical point will be the point 0 and 0. Yes. And the other critical point will be when x is equal to minus 2. F of x equal minus 2 will be equal to 1 over 2 and minus 2 power 2. Yes. E power minus 2 plus 1. Yes. And this is equal to 1 over 2 times 4 and times 1 over e. Yes. So this is equal to 2 over e. This is approximately equal to 0.7 and 5. I don't know, something. Did I compute this value? No. Maybe, let me check. 0.74 or something. Just you can take a computer and calculate it, but it's approximately that value, 0.7. Yeah. So we get the second critical point. Second critical point is, then it will be a point of component minus 2 and 0.74, something like this. Yes, so we are done with the first derivative. Then let's go for the second derivative. The second derivative. Let me take another page. And we compute the second derivative. Yes. So we have f of the first derivative, f derivative of x to be equal, it is equal to x, it was x plus 1 over 2 x squared times e power x plus 1. So then let's compute the second derivative. Let me start from here. The second derivative of x, this will be equal to the derivative of this one, and the derivative will be equal to x plus 1 over 2 x squared derivative, yes, times e power x plus 1 plus x plus 1 over 2 x squared times e power x plus 1 derivative, like this. So this will be equal to 1 and plus 2 over 2, then plus x, yes, e power x plus 1 and plus x plus 1 over 2 x squared, e power x plus 1 derivative, it is e power x plus 1, and this will be equal to 1 plus x and plus x plus 1 over 2 x squared and times e power x plus 1. Yes, so this is equal to 1 plus 2x plus 1 over 2 x squared times e power x plus 1. So this is the second derivative. This is the second derivative. We have f second derivative equal to this. This is the second derivative. And we need to find the critical points also from the second derivative. And we need to solve f second derivative of x equal to 0. When is it equal to 0? It is equal to 0 if 1 plus 2x plus 1 over 2 x squared is equal to 0. This is a quadratic function, so then x should be equal to minus, the formula is minus b plus or minus square root of the discriminant over 2a. Yeah, if we have a function of the form, this is the solution for the function of the form a x squared plus b x plus c equal to 0. If we are solving this kind of equation, then the solution should be of this form. So then we have this equation and it has the same form. We can use the same function to compute the roots. So then we will get x equal to, for in our case b is 2, then minus 2 and plus or minus square root of the discriminant. Do you remember the discriminant is b squared? B squared is 4, this is 4 minus 2a. A is 1 over 2, then minus 4a, then this is minus 2, yes, over 2a. A is 1 over 2, then 2 over 2. Yes, 2 and 2 are simplified, and then we get minus 2 plus or minus square root of 2. Yes, so we have x1 equal to minus 2 plus square root of 2. This is approximately equal to 0.58 minus, of course, and the other point x2 is equal to minus 2 minus square root of 2, and this is approximately equal to 3.4 approximately 3.41. Yes, and the critical points in this case, you need to find critical points here. You have to find image of our function at x equal to minus 0.58, and this will be equal to 1 over 2 and minus 0.5 power 58 power 2 and e power minus 0.58 plus 1, and just compute that one, find the value, and then compute the critical point also, and compute also the critical point for at the point x equal to minus 3.41. This should be equal to 1 over 2 times 0.58 power 2 and e power minus 0.58 plus e plus 1. And then find this value also. Use your calculator and find that value. And once you have those points, now we are ready to make the variation table. Yeah, let me take a new clean page. Yes. So we are going to make now the variation table. Variation table. How do you construct a variation table? When you are constructing the variation table, you need to have to know the domain of the definition, and we already know it. And you need to know the critical points. So in the variation table, we should have these things. You should have x, and x is defined from minus infinity to plus infinity. Yes. And you should have f derivative of x, and you should have the critical points for this f derivative of x. The critical points we found minus 2 and 0. Yes, this is equal to 0 and this is equal to 0. And you also need the second derivative of this function, and the critical points we found minus 3.41 and minus 0.58. Yes, so this is equal to 0 and 0 here. Yes, and what else do you need? And you need also f of x. And then you need to study the sign. Study the sign of this function at the left side of each, left side and right side of each critical point. So if we take, let me write our functions up here. Do you remember the first derivative? The first derivative was f of x, derivative was x plus 1 over 2 x squared. This is squared and times e power x plus 1. This was the first derivative, and the second derivative was f second derivative of x was do I remember it correctly? Yes, it was 1 plus 2 x plus 1 over 2 x squared and times e power x plus 1. So this was our derivatives, and of course f of x was it is 1 over 2 x squared times e power x plus 1. This is the functions that we need. So for the first derivative, we need a point which belong to this interval from minus infinity to minus 2. For instance, if we take minus 3 and we put it in this first derivative, this will be minus minus 3 and where am I writing? Yes. What am I doing? This is so weird. Clean this. Sorry for the messing up. Yeah, good. So this will be minus 3 and plus 1 over 2 times 9. Yes, and e power times e power 3 plus 1. So 9 over 2, this is 4. Then it's positive. Then we get a positive value here. this is positive, and I have checked this was negative, and this is positive. You also have to check all the signs. If you want the sign at this interval, you take, here you take a value which is less than minus 3.4, and you replace it in the second derivative, and this will give you a positive value. I've done it, but you can also do it. Here we get a positive value, and here I got negative value, and here I got a positive value. So then with this, you need you need to specify if our function is increasing. The first derivative will show us if the function is increasing or decreasing. So if you have a positive sign for the first derivative, it indicates that in that interval the function is increasing. And if you have a negative sign, it means that the function is decreasing. And if you have a positive sign, it means that the function is increasing. So now we have from minus infinity to, we have f of here, f of minus 2. Yes, and we also have f of 0 somewhere. Let me write it here, f of 0. Yes, so the function from minus infinity to minus 2, the function is increasing. And from minus 2 to 0, the function is decreasing because it has a negative value. And from 0 to plus infinity, the function is increasing. We have plus infinity here and minus infinity here. And what about the concavity? We have f of we have f of minus 3.4 somewhere here, and we have also f of minus 0.58 somewhere here. So since we have a positive sign for the second derivative, it means from minus infinity to f of minus 3.4, the function, it has a concavity, an upward concavity in this interval, and in this interval it has a downward concavity, and in this interval it has upward concavity. So the function will have this look: first upward concavity, downward, and then upward. And then like this, we are now ready to sketch our function. And the last question was to sketch our function. And how do we sketch our function? Maybe I will need to find another page so that we can be able to sketch the function. Yes, let me take another clean page. Then we sketch our function. Wow, almost done with this question. So let's try to sketch. Because when you are sketching, please sketch it well. Don't sketch it rubbish the way I'm sketching it. Try to make it very nice. But I'm also trying, but it's not easy with these tools. But since you have ruler, you will be having a ruler, you will be sketching it where we have plus infinity here in x, and this is y, and yes, and we have 0 here. Other critical point that we have, which is very important, is the point. If we have 0 here, and then let's say minus 1 here, minus 1, and minus 2 will be somewhere here, minus 2, and minus 3 somewhere here, minus 3, minus 3.4, yes, and of course minus infinity somewhere there. Yeah. And we have computed f of 0 is 0. The function will pass in this point. Yes. And the f of minus 2, we have seen that it's minus 1. Then we have 1 here. And image of minus 2, it was 0.7, let's say somewhere here. This is 0.74, yes. Then this was image of minus 2. We have a point somewhere here, yes. And the image of minus 3, of course, it will be somewhere somewhere in here. You need to compute it. And the image of the other point that it was minus 0.5458. Then it will have an image somewhere here, yes. And we have a function which has asymptote, horizontal asymptote here. We have horizontal asymptote of equation y equal to 0. So then the function comes from 0 here, and it will come asymptotically. Then it is here, this upward, then it starts turning downward. Don't know, like this. Then from here it will start turning upward. Then it will go this way. I don't know if I'm sketching it well, but it has this form. Our function will have that form. Yeah, then it will goes up here like this. Oh, not straight. This should not be a straight line. It's a curve, not a straight. Not a straight line. It should be a curve. Yeah, so it will go up somewhere here like this. So our function y equal to 1 over 2 x squared e power x plus 1. It will looks like this. Yeah, that was it. And then you get your 15 points. Wasn't it easy? Almost. Yeah, of course, when you are making a study of a function, what do you need to know? You need to know how to find the domain of definition, the asymptotes, and the first derivative and the second derivative, and how to make the variation table, and then how to sketch it. That was it. Thank you for watching today's video. Let's keep celebrate our existence and thank God for the gift of life as I'm celebrating my birthday. And I hope to see you next time. If you like the video, don't forget to click like and share the video to our network. And don't forget to subscribe if it's your first time to be on this channel. See you next time. We'll be solving the question number 17. Ciao.